Good day everyone, I am Rhea Biherona, a BSc Science student. So for today's video, I will be going to explain to you the propagation of waves. Let's define what is propagation of waves. It is a process of communication involves the transmission of information from location to another. As we've seen, modulation is used to encode the information into a carrier wave and may involve analog or digital method. It is also a characteristic of the carrier wave which determine how the signal will propagate over any significant distance. So in this video, I will describe the different ways that electromagnetic waves propagate. So before that, I will explain first what is electromagnetic wave. So electromagnetic wave is created by a local disturbance in the electric and magnetic fields. From its origin, the wave will propagate outwards in the direction. So if the medium in which is propagating, for example the air, is the same everywhere, the wave will spread out uniformly in all directions. So let's go now for the speed of sound in air, water, and solid.
Speed of sound, you have to change the properties of the medium that sound wave is traveling through. And there's two main factors about a medium that will determine the speed of the sound wave through that medium. One is the stiffness of the medium, or how rigid it is. The stiffer the medium, the faster the sound waves will travel through it. This is because in a stiff material, each molecule is more interconnected to the other molecules around it, so any disturbance gets transmitted faster down the line. The other factor that determines the speed of a sound wave is the density of the medium. The more dense the medium, the slower the sound wave will travel through it. This makes sense because if a material is more massive, it has more inertia, and therefore it's more sluggish to changes in movement or oscillations. These two factors are taken into account with this formula. V is the speed of sound. Capital B is called the bulk modulus of the material. The bulk modulus is the official way physicists measure how stiff a material is. The bulk modulus has units of pascals because it's measuring how much pressure is required to compress the material by a certain amount. Stiff, rigid materials like metal would have a large bulk modulus, and more compressible materials like marshmallows would have a smaller bulk modulus. Rho is the density of the material. Since density is the mass per volume, the density gives you an idea of how massive a certain portion of the material would be. So for example, let's consider a metal like iron. Iron is definitely more rigid and stiff than air, so it has a much larger bulk modulus than air. This would tend to make sound waves travel faster through iron than it does through air. But iron also has a much higher density than air, which would tend to make sound waves travel slower through it. So which is it? Does sound travel faster through iron or slower? Well, it turns out that the higher stiffness of iron more than compensates for the increased density, and the speed of sound through iron is about 14 times faster than through air. This means that if you were to place one ear on a railroad track, and someone far away struck the same railroad track with a hammer, you should hear the noise 14 times faster in the ear placed on the track compared to the ear just listening through the air. In fact, the larger bulk modulus of more rigid materials usually compensates for any larger densities. Because of this fact, the speed of sound is almost always faster through solids than it is through liquids, and faster through liquids than it is through gases, because solids are more rigid than liquids, and liquids are more rigid than gases. Density is important in some aspects too, though. For instance, if you heat up the air that a sound wave is traveling through, the density of the air decreases. This explains why sound travels faster through hotter air compared to colder air. The speed of sound at 20 degrees Celsius is about 343 meters per second, but the speed of sound at 0 degrees Celsius is only about 331 meters per second. So remember, the only way to change the speed of sound is to change the properties of the medium it's traveling in, and the speed of sound is typically faster through solids than it is through liquids, and faster through liquids than it is through gases.
And for the reflection, echoes, and sonic boom,
sound is a part of our everyday sensory experience. So how is sound produced?
propagated and detected? A good model is the stethoscope, used to listen to the sounds of heart and lungs. But how are these sounds heard? To understand this, we need to know what reflection of sound is. When sound travels through a medium, it strikes the surface of another medium and bounces back to the original medium. This phenomenon is called the reflection of sound, which obeys the laws of reflection. The first law states that the angle of incidence is equal to the angle of reflection. We can provide this by placing two tubes at certain angles on a wooden board. If a clock is placed near the end of one of the tubes, we can hear the sound waves through the second tube by adjusting it to get the sound at its maximum. We can see that the angle of incidence is equal to the angle of reflection. The second law states that the incident wave, the reflected wave, and the normal at the point of incidence all lie in the same plane. Sound waves also suffer reflection from large obstacles. If we stand at a distance from a high wall and clap our hands, we can hear the same clapping sound after the dying out of the original sound. This is called an echo. Therefore, for an echo to be heard, the time interval between two sounds must be 0.1 seconds. As sound travels at a speed of 340 meters per second in air, the distance traveled by sound in 0.1 seconds is 34 meters. Therefore, to hear an echo, we need to stand at least 17 meters away from the wall. Now, what happens if there are 4 enclosed walls that are less than 17 meters away? What we experience here is a reverberation that is due to multiple reflections of sound from the walls, roof, and floor, which follow so closely behind the original sound that the original sound appears to be prolonged even when the source of the sound stops. We can thus say that reverberation is the multiple reflections of sound waves, whereas echo is the single reflection of sound waves. However, excessive reverberation makes the sound indistinct, which can be a setback in auditoriums. This can be reduced by using sound-absorbing materials like ceilings made of soft and textured materials and flooring made of acoustic tiles. Certain technologies make use of the multiple reflections of sound. To name a few, we have megaphones, hearing aids, soundboards, stethoscopes, and the curved ceiling of concert halls.
A sonic boom is the noise produced by something moving through the air faster than the speed of sound. But how is a sonic boom produced? As an object moves through the air, it forces air molecules out of its way, creating waves. These waves move away from the object or propagate. If the object moves faster than these waves can propagate, the waves become more and more compressed. Eventually, they're unable to get out of the way of the moving object quickly enough and combine into one large shock wave that trails behind the object. Sonic booms come from the shock wave created by an object moving faster than its own sound waves. The shock wave forms a cone shape around the object, with the tip of the cone at the front and the base trailing behind. When you first see the object, it appears to be moving without making any noise. It's only when the base of the cone reaches your ears that you hear the boom. In order to create a sonic boom, an object must move faster than the speed of sound, about 700 miles per hour. Sometimes physicists call this speed Mach 1.
Lastly, how do dolphins, bugs, and submarines navigate?
Now consider bats, whales, dolphins, porpoises, and a few other animals that use their voices to find prey. Through echolocation, these animals emit sounds of different frequencies and loudness that bounce off the objects around them. The echoes are then captured by the ears, and the brain figures out how to recognize food and navigate the surroundings from those signals. Some bats emit sound blasts that are so loud they could deafen human hearing. Only we cannot hear their ultrasonic voices. The world would sound quite different if we could. Like whales and dolphins that use echolocation in water, Bats use their voices to see the world through air, and very effectively. A katydid rests motionless on a leaf, one of thousands of leaves on a tree. The insect doesn't make a peep. The night is black. A leaf-nosed bat flying nearby blasts the tree with sonar at ultrasound frequency, then listens. It sees the katydid with the echo created from sonar and swoops in for the kill. No human-made sonar equipment can detect objects with such finesse. In fact, the most sophisticated submarine sonar system, large as a house, cannot see the world nearly as well as a bat. Leaf-nosed bats are at the pinnacle of echolocating animals. Their fleshy noses are like musical instruments that amplify and focus the sounds made with their larynx. In fact, their noses change shape to produce different sounds for scanning different objects in the surroundings. Their ears are also capable of shape-shifting to capture the sensory information they need at any moment, so they can fly in the dark without hitting tree limbs or power lines, communicate with each other, and pick an insect meal from dense vegetation with surgical precision.